Okay, so we're talking about inverse functions. So they're a special kind of a function that has to have a one-to-one function in order to have an inverse. It's not just a function, but a special function. So this is the requirements. First is it's got to be a function. So the test to see if something is a function is every element of the domain has paired with only one element in the range. Typically, we call this a vertical line test if you're looking at a graph, but you need to understand both points of that. And the second part of being one-to-one, there's really two requirements, is that every element in the range is paired with only one element in the domain. So this is called the horizontal line test if you're looking at a graph. So let's look at this first function. This is not a graph, of course. This is domain values here, paired with range values here. First, let's see, does it pass the vertical line test? Is it a function? And then we'll see if it's a one-to-one function. So each element of the domain is paired with only one element of the range. So 2 is paired with 7, 5 is paired with 7, 8 is paired with 3. Each element of the domain is unique. It has a partner. So it does pass this test. This is definitely a function. Second test is saying every element of the range is paired with only one element in the, so that was true. Every domain had only one partner. Is that true about the range? Especially talking about number 7. So 7 seems to have a partner with 2 and 5 here. So they're paired with more than one. So this is not a one-to-one function. So it's a function, but it's not one-to-one. Let's look at this one. So it does pass the vertical line test. If you kind of move that point along, it only crosses at one particular spot. But if you turn it and make it a horizontal line test, you're going to test it, you're like, nope, doesn't seem to work. It's not a one-to-one function at all, so it doesn't pass that test at all, because if you look at it, it's got, like in this case, it's got the same y values, 3.03, but two different x values. Because those are different, just that one point proves it. Those 2 points prove that that is not a one-to-one special function. Okay. So inverse functions, so this is the look of them, and be careful with this notation. It does not mean negative exponent. That's what you might be used to saying. When you see f to the negative 1 power, you're like, oh, it's just a negative exponent, brings it down to the denominator. It's not what happens. So this does mean the inverse. So we use this notation when we're talking about f's or g's or h's, where f of x, talking about functions, that means the inverse of a function. So let's first look at it graphically, and then we'll look at what it looks like algebraically here. So if you look at it graphically, so like if you say some of these points, like these are x and this are y, so like that's the point 2, 2, so 2, 2. That's the point 1, 0. That's the point 0, negative 2. That's the point negative 1, comma, negative 4. And that's the point negative 2, negative 6. And there's a few more, about 4, comma, or that's actually what, 3, comma 4. And 4, comma 6. So those are all the points on that line. There's a line here called the identity line. So this line right here is that line in the middle. It's the dotted line. So this is the line y equals x. It's a dotted line, has a slope of 1. It goes through the origin there. And that's always the same line. So that's always the identity line. And what you do basically is you reflect any function over the identity line. It will form the inverse function. So let's see if that happens here. So I'm going to just put down some points. Like you can see this point right here at 1, 0. If I reflect it over the line, it looks like it goes to about there. Let me just kind of get rid of that point so you don't see it. So it looks like it goes about there. And so that would be the point 0, 1. So 0, 1, let's write that down. So 0, 1. If you take this point and reflect it over, it looks like it was at 3, 4, and now it's at 4, 3. So that's going to be 4, 3. This point was at 4, 6. Now it's going to be, if I go diagonally across that line, that's going to be 6, 4. You might notice a pattern here. This point actually reflects, it's on the reflection line, so that's still 2, 2. The x's and y's did actually switch places. That was at 0, -2. Now it's going to be at -2, 0. Hopefully you're seeing the pattern. Instead of -1, -4, it's going to be -4, -1. Instead of 0, -6. I'm sorry, instead of -2, -6, it's going to be -6, -2. Can you see all the x's and y's kind of flip-flopped, right? If you look at the original list here, exactly what happened in that line is called the identity line. So it's a reflection over the line y equals x, which is called the identity line. So the inverse is that red line. So this is the, if f is the original function, this is the inverse of x, of f. And there's one kind of trick question here. I just want you to see it. I think it's kind of an interesting one. So let's say you're given this. By the way, you plug x into a function. The output is your y value or your f of x value. So this is actually the ordered pair -1, -4, if you think about it. So the inverse, what's the big idea of inverse? Let's think about that again. So we're switching, x's and y's are switching spots. So all the, you see -2, 6, -6 is now -6, -2. -1, -4 is now -4, -1. All the x's and y's switch spots. So that's the big idea. Instead of doing f of x, this is actually f of y equals x, right? So it's saying what value is x when y is -4. Well, when y is -4, x is -1, so this is going to be -1. That's it. So that's the only point you know on this graph actually is the point that reflects. In this case, the x's and y's will switch. If you know that much about the concept, you'll get that question. So the function kind of undoes whatever the original function was. I want you to get the concept first, then we'll work out how to actually work it. So if I wanted to find the inverse function of this function, if the original function is 2 times x, the inverse would be x divided by 2. So the inverse of multiplication will be division. Now, it's not always that easy. That seems really easy, actually. But, I mean, the concept there, if the original function is adding 2, then the inverse of that function would be to subtract 2, bring it back to normal. So find the inverse. So the big idea here, again, of inverses is we're going to switch x and y. So your steps to do this are first write it as y equals. So right now it's f of x equals. It's going to help you to have a y in there. Second step, big idea of inverse. Inverses switch x and y. So this becomes x equals 3 minus y over 4. Solve for y. So multiply both sides by y. I'm sorry, by 4. Because it's a 4 down there. I almost couldn't read my writing. So multiply by 4. It cancels. You get 4x equals 3 minus y. Subtract 3. Get 4x minus 3 equals y. Negative y, actually. Divide by negative. You get y equals negative 4x plus 3. So I divided by negative there. And last step is to write it as f of x equals. We started by saying y equals, and now we're going to change it back to f of x, or whatever the function's name is. See if it makes sense. So the original function is we're subtracting from 3. Now we're adding 3. We're divided by 4 in the original. We're multiplying by negative 4. So it's kind of related there. It gets a little confusing at times. That's why this method really helps. So I think this 4-step method that really helps you solve and find the inverse algebraically. Let's find the inverse of this one. So first step, y equals 2x plus 1. Switch the x and y. Subtract 1. Divide by 2. and you get y equals that. Here's your final step. I should have written it this way. I probably should have said it this way. It's really the inverse. So you want to name it by its name. So let's call this, instead of f of x, this new function is called the inverse of f of x equals x minus 1 over 2. And that makes sense. Instead of adding 1, we're subtracting 1. Instead of multiplying by 2, we're dividing by 2. So in the context, that actually kind of works. Find the inverse of this one. This is a really challenging one. I'm not sure if I'll give you one this hard, but I want you to see a really difficult one and see kind of what happens on this one. So we're going to start normal. We're just going to do it, see what happens. X squared plus 3. Switch x and y. Subtract 3. Take the square root of both sides. Don't forget, plus or minus. You get y equals, or the inverse of y, so to speak, equals plus or minus square root of x minus 3. Now the problem is the domain was restricted. And it's actually a good thing that domain was restricted. If you look at this original function, y equals x squared plus 3 looks like this, basically. Looks like that, has a y-intercept at 3. But it says we don't want that whole function. We only want it when x is greater or equals 0. So there's kind of like a closed circle there. It starts at 0 and the domain goes up and to the right. I mean, the domain goes to the right forever. So that's the domain of that function. In fact, it might help us to write out what the range is. Just looking at it, you can tell the range. It goes as low as 3. So y is greater than or equal to 3 on the original function. Right? It's going to help us to think about the domain and range of the original. By the way, why did they restrict the domain? I just want you to understand this, because if it had been a full parabola, that's not a one-to-one function. It doesn't have an inverse. We want to have an inverse here. So they said, well, let's just do half the parabola. Hopefully that has an inverse. So if you think about the domain and range of this function, the big idea of inverse is they're going to switch places, right? So the domain was x greater than or equals 0. Now the range is y greater than or equals 0. It's going to flip. The range was y greater than or equal to 3. Now the x value is x greater than or equal to 3. So when you look at this particularly, you know that this can't be negative here. So the actual answer, the inverse, is going to be just the positive case there, x minus 3. If you look at the graph of this, it goes 3 units to the right. It looks something like this, roughly, is the square root function. But the domain is restricted to x greater than or equal to 3. That's why it starts there at 3. The range is only when y is above 0, not below 0. So that's kind of where that comes from. Find the inverse. We just did that. Let's look at what that was. X minus 1 over 2. X minus 1 over 2 is the inverse of that function. I guess we got f to the negative 1. Now find the value of this. Okay, so this is going to be the inside function is the inverse. So I'm going to plug 2 in right there for x. So 2 minus 1 over 2 is 1/2. F of 1/2. Now I'm going to plug the 1/2 in right there. Half of 2 is 1. 1 plus 1 is 2. And we got it. Let's try this one. So let's do different question. What's the inverse of f of x? So the inverse of f of x is really 2x plus 1. So I'm going to plug that in. Now, everywhere there's an x right there, I'm going to plug in the 2x plus 1. So I get 2x plus 1 minus 1 all over 2, which is 2x all over 2, which is x. Let's cancel. So all that simplifies to be x. Kind of interesting. Okay, last problem, graph the inverse of that one. So let's try to do it graphically and then we'll solve it algebraically just so you're getting it. So the original function has a slope of -1/2 up 1/2. Looks something like this. Try to draw straight lines and done smart one. Okay. That's the graph of the original line. We have what's called a identity line. Right there. It's not bad. I mean, for just a freehand of it. I could try to do better. Let's see. That's beautiful, I'd say. Okay, so we have that one. So let's find the inverse of this function graphically, see if we can find it. So this point's going to be the same, right? It reflects right on the reflection line, the identity line. This point will reflect over to here, I believe. Let's see. Yep. This point will reflect over to here, so this one goes to here. This point was 6, 0, now it's 0, 6. Okay, I like that. This one was 0, 3, now it's 3, 0, I got that. This was -2, 4, now it's 4, -2. This was -4, 5, now it's 5, -4. I think that's plenty of points probably. Looks like that. This is the inverse. If this is f, this is inverse of f. The algebraic way of finding the equation of that line would be to switch x and y, solve for y. I'd probably multiply everything by -2. If I do that, I get y equals -2x plus 6. That does look like the equation of -2x plus 6. And that is the inverse function there. Usually use it with function notation. I'm not sure you can use it with y, but that's the idea. Okay, we have a couple more minutes. Oh, no, actually, that's about it for today.